Imagine a world where ships predict their own breakdowns and ports operate with flawless precision, all before they even happen.
Welcome to the deep dive. Our mission today is pretty focused. We're going to take this concept of the digital twin in the maritime industry, try to strip away all the glossy marketing, and really analyze the harsh technical reality of what it takes to make this work.
I think we have to start right there. We need to completely recalibrate what you, the listener, probably think a digital twin is. Because most people, when they hear that term DT, they're picturing a sleek 3D model of a ship on a screen.
Exactly, a virtual replica.
But our source material is really clear on this.
hmm
If that's all you have, you are, and I'm quoting here, fundamentally still in the digital Stone Age.
That's the critical misconception, and we have to tackle it head on. The industry, in its rush to use the buzzword, has really confused what a true high-maturity digital twin is. A static 3D CAD model or, a building information model, a BIM, that is not a twin.
They're just precursors.
They're precursors, yeah. Our sources call them low maturity stages. Maybe a level 1, which is just replication, or what they call a digital support system. I mean, that's often just a static record someone has to manually update in a database.
Okay, so if having this perfect virtual model isn't the point, what is?
Yeah.
What is the core technical definition we need to stick to? Where's the line in the sand between a fancy animation and a real functional digital twin?
The single defining criterion is bidirectional data flow and the continuous synchronization that supports.
Bi-directional, so two-way traffic.
Two-way traffic, constantly. A true DT has to continuously link the digital model with the physical thing. That's the phygital focus they talk about. Data flows from the ship's IoT sensors to the model maybe 100 times a second, but, and this is the crucial part, the model then processes that, runs its simulations, and sends optimized commands back to the physical asset.
That's a huge distinction. So we're not just passively watching a temperature gauge on a screen.
Right.
We're talking about getting to what they call level 4 maturity, which is real-time interaction, and then the ultimate goal, level 5.
Which is autonomous closed-loop control.
And that requires a level of trust in the data that is just. It's orders of magnitude higher than anything standard in the industry today.
It really is. And this isn't just some academic classification. This has real legal and regulatory teeth. The big classification societies like ABS and DNV, they're defining the DT as the indispensable central nervous system for autonomous ships.
The MCNS.
Right. They see that if a vessel is going to operate without a human in the loop, the DT has to function as the proof of equivalence mechanism.
A proof of equivalence mechanism. Okay, unpack that for me.
It just means the automated system has to be proven to be as safe or, safer than a human crewed vessel. And to prove that, the DT has to be the absolute verifiable record of reality. It serves as a kind of super sophisticated, tamper-proof verifiable data recorder, or VDR.
So like a plane's black box, but it's live.
Exactly, but running live and providing forensic level detail for legal defensibility. It means every single piece of data going in and every control signal coming out has to be validated and logged with the highest possible integrity. The bar is being set incredibly high.
It really is. It completely shifts the conversation from how cool does the graphic look to how dependable is the math. Okay, so let's move from the concept to the concrete. Let's look at the ship itself. When you put a digital twin on a vessel, you're basically turning it into a floating data center.
A floating intelligent platform, yeah. A huge distributed edge computing device.
Right.
And that's the critical shift. The vessel's DT merges all its technical specs, the deep component models, and we're talking about things like finite element models or FEMs that simulate structural stress, with this continuous high-volume data feed from maybe thousands of sensors.
And it has to run on the ship itself. That's the edge computing part.
It has to, because these are mission-critical processes. You can't tolerate the slightest connectivity lag when you're dealing with the main engine.
So, okay, the economic heart of this is always going to be fuel. That's where the money is. Traditional methods use, historical tables?
Averages.
Right. They look in the rearview mirror.
Yeah.
Old models, like a basic speed power curve, are static. They lag behind reality, especially when the weather turns. A DT gives you instant decision support using these predictive models.
But that means the model has to be incredibly accurate.
Oh, extremely high fidelity. You need accuracy that minimizes uncertainty, and just as important, the computation has to be efficient. The crew on the bridge needs the answer, the recommendation, in time to actually use it.
And I appreciate that our sources don't just wave their hands and say AI. They get into the specific architecture you need for this kind of forecasting. Let's talk about the neural network they use for fuel oil consumption, or FOC.
Right. The model that's been identified as really effective for this is a bidirectional long short-term memory network, a bi-LSTM.
And this isn't some generic machine learning thing. Predicting fuel use is a classic multivariate time series challenge. A basic model looks at what's happening now to predict the next step. A standard LSTM looks at the recent past. The bi-LSTM is better because it looks at the sequence of data, both forwards, from past to present, and backwards.
And why is looking backwards and forwards so important for something like fuel burn?
Because a ship's performance is all about context.
Hmm.
The fuel you're burning right now isn't just because of the wind 5 minutes ago. It's also about the wave action you're expecting in the next hour and the trim change that happened over the last hour. The bi-LSTM is just really powerful at capturing those long-term dependencies. It gives you a much more robust prediction.
And what's this model actually eating for data? I mean, it must be way more than just a GPS point and speed.
Oh, way, way more. The inputs are incredibly complex. You have all the navigation data, speed, course, heading. Then the operational conditions like ship draft and, this is a big one, trim, main engine shaft power. And then you have the really specialized Matosian data.
Matosian. So that's the weather, the ocean conditions.
Exactly. Real-time and forecasted wave data, wind speed and direction, currents, even air temperature. When the DT can accurately combine a live weather forecast with the bi-LSTM's predictions about the engine, that's when you can really start to nail down the fuel consumption estimate. Because bad weather is the biggest variable, always.
And integration, the Matosian data, is what lets the system go from just predicting what will happen to prescribing what you should do.
Yeah.
And that's the whole point of just-in-time route optimization.
It is. It's the jump to prescriptive analytics. The DT enables JIT routing by combining those FOC models with really advanced weather routing algorithms. The result isn't just the fastest route, it's the optimized route that minimizes cost and time together.
How does that algorithm actually find the best path?
It generally uses something called the isochrone principle. You can think of it like this dynamic map. At any point, the algorithm calculates every possible place the ship could be in, say, the next hour. Given different speeds and courses and the real-time weather, it builds this massive graph of possibilities around your planned route, constantly finding these small deviations in course and speed that keep you on the most efficient path.
And it's integrating things that a busy crew might overlook, like trim.
Yes, and that's a huge deal. The system is doing real-time trim optimization. Now, trim, that's just the angle the ship sits in the water, is critical for efficiency. But optimizing it manually involves these really complex calculations that, frankly, crews often simplify or just ignore because they're overloaded.
But the DT does it automatically.
Continuously. It refines the fuel estimates by integrating that real-time trim with data about the hull's condition, and it might recommend a tiny ballast adjustment that shaves, a few % off the fuel burn. It seamlessly folds in a factor that was often just too much of a hassle before.
That's incredible fidelity.
Mm-hmm.
But I have to imagine that getting all those sensors to talk to each other and send clean data from the middle of the Pacific, that's where the real nightmare begins.
Yeah.
All that math is useless if the data is garbage.
That is the big reality check. The accuracy of the whole system, especially that bi-LSTM model, depends 100% on data quality. If you have bad data missing values, outliers, a sensor that's drifting, you'll get bad simulations, bad predictions, and ultimately, catastrophic autonomous actions. That's the data ops challenge at sea.
So what are the non-negotiable steps to make sure that data is clean before it hits a high-stakes model?
It's a really rigorous, multi-stage process. You start with basic data integration, just getting everything into the same format. Then you move to things like missing values imputation, basically filling in the gaps when the signal drops, and noise identification.
What's an example of noise identification?
It's about filtering out unrealistic values. Say your engine log shows a shaft power reading that is physically impossible for that engine. The system has to know the physical limits of the equipment and just throw that data point out. And for more subtle errors, you need statistical methods, like Chauvenet's criterion.
Chauvenet's criterion. That sounds like a very fancy way of saying outlier detection.
It is, but it's that mathematical rigor you need. It calculates the probability that a given data point is just a random error based on the mean and standard deviation of the data around it. If the probability is, say, less than 1 in 100 that it's a legitimate value, you cleanse it. If you skip that step, your autonomous system is making life or death decisions based on fiction.
This all explains why the ship has to be an edge device. Why not just beam all this raw data to a massive cloud server somewhere? It would seem cheaper.
The physics of latency. It's non-negotiable. For mission-critical stuff like propulsion or collision avoidance, you need an instant response. You just can't rely on a satellite link back to a data center thousands of miles away. The lag, the potential for signal loss, it's just too risky.
So the ship has to think for itself, especially for autonomous functions where a half-second delay could be the difference.
Exactly. The decision model has to run locally. Plus, can you imagine the cost of sending terabytes of raw sensor data over satellite every day? It's much more economical to process it on the ship, condense it, and just send back the key insights or the summary to headquarters. The vessel has to be computationally independent for safety and for cost.
We've set up the vessel as this hyper-connected, self-optimizing system. Now let's zoom in on the most critical parts, starting with the heart of the ship, the engine. What can a digital twin do for managing the health of a huge marine diesel engine?
Well, this gets us squarely into predictive maintenance, or PDM. And you have to remember, maritime maintenance has been historically pretty inefficient. You had reactive maintenance.
Wait until it breaks, then fix it.
Exactly, leading to crazy downtime, emergency costs. Then you had preventive maintenance, where you replace parts on a fixed schedule, which often means you're throwing away perfectly good, very expensive components.
And PDM uses foresight to change that.
Precisely. The DT driving the PDM system uses real-time monitoring to calculate the probability of a future failure. The whole goal is to intervene just before something breaks, so you maximize the life of the part but avoid that unscheduled downtime. And for something like a marine diesel engine, which is under enormous stress 24/7, that's vital.
So how does the DP model actually predict that a part is starting to degrade, especially with all the noise from a massive engine?
Well, the predictive intelligence is getting much more sophisticated. For something as high stakes as the engine, the specific AI approach highlighted in the research is something called an auto-associative kernel regression model, an AAKR.
AAKR model. Okay, that sounds like jargon, but it's the key piece.
It is, and what's so interesting about it is how it's trained. You train it only on historical data from when the engine was running perfectly, in a totally fault-free state.
So it learns what normal looks like. It's like learning someone's healthy voice, so you can immediately tell when they sound sick.
That's a perfect analogy. The model builds this incredibly detailed statistical fingerprint of healthy. The moment the live data stream deviates from that baseline, the alarm goes off. It doesn't need a specific fault code. It just knows this isn't normal anymore.
And it's looking at dozens of sensors at once to build that fingerprint.
Right. The studies we saw mentioned systems using up to 46 sensors monitoring rotation, temperature, pressure, vibration, all at the same time. When that 46-dimensional pattern shifts away from its healthy state, the system flags it, often way before a simple higher-low temperature alarm would ever trigger.
Beyond just breaking down, there's also huge regulatory pressure on emissions, especially NOx. Can the DT handle that kind of complex environmental modeling?
It has to. I mean, with rules like the EEXI and CII, it's a must. But you can't do it with simple models. The reason is that nitrogen oxide, aloxox, its formation, is incredibly sensitive. It doesn't just depend on the average temperature inside the cylinder. It depends on these tiny, localized hotspots and the way the flame front moves.
So a simple model that just averages the conditions in the cylinder is going to miss the mark.
It misses the granular detail completely. Those are called single-zone models. They're cheap to run, but they can't accurately predict NOx. To get the kind of accuracy you need for regulations, the DT has to run what are called phenomenological multi-zone combustion models.
That sounds computationally heavy.
It is. These are complex, physics-based models that split the combustion chamber into multiple virtual zones. They account for all those localized effects, the hotspots, the air-fuel mixing. It takes a lot of processing power and a ton of calibration, but the payoff is huge. The DT can then accurately simulate the impact of switching to alternative fuels like LNG or methanol. It moves the discussion from a spreadsheet guess to a verifiable simulation.
Okay, let's move from the engine to the hull itself. A ship is under constant dynamic stress. How does the DT keep an eye on the structural integrity of the vessel?
The core technology here is the finite element method, or FEM. This is absolutely critical engineering, and FEM model simulates how the entire ship's structure, the hull, the decks, deforms and behaves under all those changing loads from waves, wind, and cargo.
And that's what prevents a catastrophe.
That's the goal. The FEM breaks the entire structure down into thousands of little pieces or elements. By calculating the stress and strain on each tiny element, the DT can find weak spots, perform fatigue analysis, and generate a continuous health report on the ship's structure. It lets you find a potential failure long before you'd ever see a physical crack.
That handles the big structural stuff. But the sources also pointed out this kind of slow, quiet problem that costs the industry billions. Biofouling. That's slime on the hull.
Biofouling is a massive hidden tax on shipping. It's incredible. Even a thin layer of sludge can increase fuel consumption by 20 to 25%. It's a huge economic and environmental cost. So cleaning the hull isn't optional, it's an imperative.
And how does the digital twin make that cleaning process smarter than just sending a diver down every 6 months?
It brings automation and precision. The DT has that perfect 3D model of the hull. That geometric data is fed directly into the path planning for automated cleaning robots. It's a process called CAD-to-path programming. The robot already knows the exact shape of the hull before it even touches the water.
And the assessment of the fouling itself becomes objective, not subjective.
Absolutely. It's a high-tech assessment now. The robots use AI algorithms that are processing images from high-res cameras and spectrum sensors. They can actually distinguish between different types and thicknesses of marine growth. So you get this objective map of the problem, which totally removes the human error you get from a simple visual inspection.
I thought the geographical part was fascinating. The model isn't just looking at the hull, it's looking at the ship's travel history.
Right, because the growth rate of that biofouling depends heavily on water temperature. So the DT model tracks the change in sea surface temperature, the delta SST, based on the ship's route. It uses that to predict the growth rate and assess how much life is left in the anti-fouling paint. It allows you to schedule cleanings proactively based on risk, instead of just using a dumb, fixed schedule.
So we have this incredibly smart ship, but that efficiency disappears the second it has to wait outside a port. So let's talk about the port. What does a digital twin look like when it's managing a massive piece of infrastructure?
The focus of a port digital twin is completely different. It's all about complex orchestration, resource management, and safety. The challenge isn't one engine. It's managing thousands of assets, cranes, berths, trucks, and optimizing the flow of cargo across this huge, constantly changing area.
Can you walk us through some of the real-world examples from the sources?
Sure, let's look at the early adopters. The port of Rotterdam, back around 2017, they were mainly focused on creating a precise digital copy for visibility. They wanted to track ship movements, weather, and infrastructure status to just improve their overall planning. Same with the Port of Hamburg, which used their twin to monitor things like the big Kolbrand Brook Bridge to predict its maintenance needs.
And in the Port of Singapore, which launched its twin in 2025, what was their focus?
Singapore went really heavy on advanced geospatial tools. Their main goal was integrating huge amounts of data satellite imagery, live traffic, weather forecasts, local sensors into these really detailed 2D and 3D visualizations. It was all about having this complete real-time spatial truth of the harbor, especially for planning complex operations like bunkering new alternative fuels.
And what about managing the really high-risk stuff, like dangerous cargo?
That brings us to the Shenzhen port example, which is fascinating. Their DT is laser-focused on safety and risk assessment for dangerous goods containers. Their models can predict how environmental factors, temperature, humidity, pressure, will affect the hazardous materials inside, and the accuracy they're getting is just astounding. The correlation coefficients are up to 0.9855.
Which means the digital model is an almost perfect mirror of the physical reality.
Exactly. And that's the level of trust you absolutely must have before you can even think about automating the handling of dangerous goods.
That precision is key. But the biggest win comes from syncing the ship and the port. That's the goal of just-in-time arrivals.
JIT is the holy grail. It means the port twin has to be in constant dynamic communication with the ship twin. The goal is simple. Eliminate waiting, reduce handling time, reduce port stay time. Because minimizing that idle time has these just staggering benefits.
The sources quoted a huge number for the environmental impact.
Yeah, over 75% in carbon emission savings. Just from eliminating that wasteful practice of ships racing to a port just to drop anchor and burn fuel for days waiting for a berth. The DT orchestrates it so the ship slows down way out at sea and arrives precisely when the port is ready for it.
A 75% saving is massive. What's the biggest hurdle stopping every port from doing this right now?
It's the sheer computational complexity of the scheduling. This involves solving what's known as the berth allocation problem, or VAP.
And that's what they call computationally intractable.
Right. The BAP means you have to assign a berth and a service time to every single incoming ship, but you're trying to optimize for multiple conflicting goals at once. Minimize service time, maximize key usage, manage your cranes and tugs, and you have to do it in real time while everything is constantly changing. Weather, delays, breakdowns, it's a scheduling nightmare.
So traditional methods methods just can't keep up.
They can't. This is where the DT framework, with its real-time data and advanced algorithms, becomes the only way to even attempt to solve it. It's moving ports from being reactive to proactive.
So from emergency response to planning and prevention.
Exactly. The DT moves the port from responding after an accident happens to planning before it can. And looking ahead, the next big step is scaling this up beyond just one ship and one port.
To a whole supply chain.
That's where you get into federated digital twins. This is where the vessel DT talks to the port DT, which talks to the rail terminal DT, which talks to the trucking DT. They all form this secure, interconnected data ecosystem.
And that enables what? Synchromodal logistics.
Exactly. When a disruption happens, say a rail line closes, the federated system has the real-time data to dynamically reschedule and reroute cargo across different modes of transport. It gives you a level of supply chain resilience that is just completely impossible in today's siloed world.
Okay, we've covered some incredibly powerful and technically demanding systems, but you said at the top that most of the industry is still stuck at the low end of the maturity scale. So where do things actually stand right now?
Well, if you use that 6-level model, most of what's out there today is still between level 0 and level 3. They're either static models or they're connected to data but just doing passive monitoring or maybe some isolated simulations. The real goal, that level 4 bi-directional control and level 5 full autonomy, that is still largely aspirational for the industry as a whole.
So it feels like we're leaving the hype cycle and entering the really hard, expensive engineering phase. What are the big roadblocks stopping the industry from getting to level 5?
The research points to 4 big intertwined challenges. The first is just fundamental connectivity. You need strong, reliable, high bandwidth communication that works in the middle of the ocean. Without that, the whole concept of a real-time DT just falls apart.
Makes sense. If the brain can't talk to the body, it's useless. What's number 2?
Data standardization. It's a fragmentation problem. Every equipment manufacturer, every fleet, they all have different sensors and data formats. It makes it impossible to build scalable AI models that work across the industry. It's just chaos.
And then you have the non-technical barriers,
which are often the hardest to solve. Number 3 is high costs. The investment in all these sensors, the edge computing, the data scientists, it's a huge barrier, especially for smaller companies.
And the last one, the human one. Human adoption.
The silent killer. You have crews with decades of experience. If they don't trust or understand the system, they'll just revert to the old manual ways. The systems have to be designed to be usable and explainable so people can actually build trust in them.
Let's talk about the biggest stake here, security. When the DT becomes the central nervous system, it's also a massive target for cyber attacks. How do you make these systems resilient when a hack could literally sink a ship?
Cybersecurity has to be baked in from the very beginning. The threats aren't just hacking the software, it's manipulating the sensor data to trick the system. So the DT has to also act as its own defense mechanism. It has to be a physics-based truth engine.
A truth engine. How does that work?
The DT's physics models know what should be happening. They know the stress limits, the normal operating temperatures. So you use advanced filters, like augmented state Kalman filters, that are constantly comparing the raw sensor data to the physical reality predicted by the model.
So if a hacker injects fake data, say reporting the engine is at 10,000 degrees, the filter would know that's physically impossible.
Exactly. If the incoming data violates the laws of physics, the Kalman filter flags it instantly as malicious or faulty. It prevents the system from acting on that bad data. It keeps a verifiable link to reality at all times.
So beyond all this incredible tech, what's the bottom line? What's the economic imperative that makes this unavoidable?
The ROI is just staggering. The studies project up to a 40% reduction in ship operating expenditures from better maintenance and efficiency, and up to a 30% decrease in port time from JIT arrivals.
And the regulatory pressure you mentioned.
Yes. The DT is becoming a tool for survival. You can't comply with new emissions rules like EEXI and CII without this kind of high-fidelity simulation. You have to be able to accurately model the impact of switching to a new fuel. It's not just about saving money anymore, it's about being allowed to operate at all.
So we've established that a digital twin isn't defined by how it looks. It's defined by its rigorous, real-time, bi-directional data flow. It's the complex cyber-physical nervous system for the whole maritime industry.
And the standards that are being set for these autonomous systems, the continuous validation, the forensic readiness, they're creating a whole new level of expectation. And that brings up a final provocative thought for you to chew on.
The level of data integrity and technological integration we're demanding for a level 5 autonomous system. It already exceeds what we legally require from many human-operated systems today.
So if the DT is the legal and classification equivalent for an autonomous ship, does this mean that the legal standard for data integrity and tamper-proof logging on these future robot ships will soon surpass the regulatory demands we place on human crews? We're setting a new, higher standard for verifiable truth at sea.
So think about that. As we move forward, which part of this massive ecosystem, the vessel's performance, the engine's health, or the complex dance of the port, will be the first to actually overcome all these barriers and reach that true Level 5 autonomy? It's something to consider as the industry moves from hype to hard engineering. Thanks for joining us for the deep dive. We'll see you next time.